I'm Karen Carniel, Deputy Editor at CSHL. We're here at the 79th Cold Spring Harbor Laboratory Symposium on Quantitative Biology. This year's topic is Cognition. And I'm very pleased to be here with Richard Axel from Columbia University. Richard. So, you've been interested in how odor is represented in the brain. And one of the things you've been thinking about and talking about recently is differences between innate odors and how they're represented and learned odors and how they're represented. Can you talk about that?
Yeah, a relatively small number of odors elicit innate, aversive, appetitive, social, and sexual behaviors. But most odors are not innate. The valence of most odors is learned. And I think it's reasonable to believe that innate odors are mediated by neural circuits that have been put in place in response to predictive cues that have existed over long periods of evolutionary time. They're determined. Learned odors, on the other hand, are elicited, we believe, by ensembles of neurons that are reinforced to acquire meaning over real time, that is, over the life of an organism. And what we've been able to demonstrate is that the olfactory information, once it leaves the first relay, the olfactory bulb bifurcates, or it really pentafurcates, splits into 5. And one of the regions it projects to is a region called the cortical amygdala, which recently we've shown is both necessary and sufficient to elicit innate behaviors. Another of the projections goes to olfactory cortex, piriform cortex. And that ensemble, we believe, is not innately determined, and that ensemble is required for learned olfactory behavior.
So there's perhaps a greater degree of functional plasticity in the piriform than would be seen in the amygdala?
Yeah, that's a very elegant consequence of the way the piriform representation is generated. That is, we believe that this representation is generated by virtue of receiving inputs from random combinations of glomerular loci in this first relay, the bulb. And if it's random, if the representation is indeed random, it can have no meaning. And so meaning must be imposed by experience. And so the system is set up to require this plasticity in order to elicit a learned behavior. And of course, the enormous benefit of this is that a representation is generated and it has no inherent bias with respect to behavioral output. It has no valence, and valence being imposed by learning allows the organism not only to respond to the universe of odors, but to be able to respond in a way that allows an appropriate behavioral response to an often very variable and unpredictable world.
One of the initial striking findings on olfactory neuron projections was that there is this striking topographical organization at the first layer, the olfactory bulb. So was it initially surprising to you that that's sort of lost when you go to the peer form, or looking back, does it make sense that you'd want to preserve that globally, even though you're going to lose the meaning it might have imposed at the next level?
Yeah, being an amateur neuroscientist, I was quite struck by the fact that Piriform discards this order so early in the pathway. I think that the idea of inputs from random sources to neurons in sensory cortices is going to be much more general than simply piriform cortex. I think that we're going to see it, but we're going to see it in higher stations of sensory cortices. In piriform, you see it after 2 synapses. So indeed, I was surprised, and it forced us to think about what advantages it affords the organism. And in fact, if you model a random representation, and we have with Larry Abbott at Columbia, there are many advantages to random inputs that would not emerge with more structured inputs.
Are there, have you encountered those in the field who disagree with your interpretation of random inputs and imposition of meaning, and what do they say if that's the case?
I've encountered more people that question our interpretation than agree with it, but gradually that's beginning to shift as more and more data emerges. Their argument is in the olfactory bulb, a given odor activates a stereotyped spatial pattern of neural activity. And we don't see that in piriform. We see distributive activity. All odors give a dispersed pattern of neural activity, which is interdigitating for different odors. There's no discernible order. So the critics would argue that I do not know the true, natural, salient odor mixtures that are relevant to the organism. And were I to be able to identify those, I would see a maintenance of order in some form. It will be transformed from the tight insularity of the bulb. But every effort we've made to discern odors or mixtures of odors that would restore order have failed. We've tried to address the criticisms.
So since we're talking about innate versus learned, and the topic of the meeting is cognition, I thought I might ask you what might be more of a philosophical question, which is there anything such as innate cognition, or is that an oxymoron?
I think that the way in which the brain thinks, that is, the material of cognition, is likely to be innate. And there's something probably uniquely human about the materials we use. By materials, I mean the neural circuits that we use to think, to carry out what some people call cognition. I'm incapable of it, but the rest of the world does it very well.
Richard, I've noticed that you like to use artwork as analogies for neural representations. To end the interview, can you just tell us a little bit about your thought process there?
My thought process is very simple. Art matters.
Thank you very much.